So very good afternoon to all of you. I am Dr. Keshav Walia. Presently, I am serving as an associate professor at DAB University, Jalandhar. So I am firstly thankful to organizers for inviting me for attending this stimulating event. So I am here to give a talk on nonlinear interaction of high-power laser beam with plasmas. So this is the outline of my talk. Firstly, I will discuss about introduction to plasma state, then nuclear fusion in stars and ways of achieving nuclear fusion on Earth. Then I will discuss about role of laser plasma instabilities in inertial confinement fusion, then self-focusing mechanisms, harmonic generation, and finally I will discuss the impact of self-focus high-power beam on second harmonic generation in quantum plasmas. So plasma is a quasi-neutral gas of charged and neutral particles that exhibits collective behavior. So matter in the universe mainly exists in four states, namely solid, liquid, gases, and plasma. Whenever solid is heated, then it undergoes transition to, Whenever solid is heated, it undergoes transition to liquids. Whenever liquids are heated, then it undergoes transition to gases. And when gases are heated at extremely high temperature of the order of 10⁵ Kelvin, then electrons get stripped from their respective nuclei, resulting into formation of ions and electrons. This ionized state of gas is known as plasma. In fact, we live in 99% of the universe is in plasma state. That is in the form of liquefied gases with atoms dissociated into ions and electrons. In fact, we live in 1% of the universe in which plasmas do not occur naturally. The reason for this can be seen from the Saha's equation, which tells us about the amount of ionization to be expected in a gas at thermal equilibrium. If I take ordinary air at room temperature by selecting these parameters, then the number density of ions to that of neutral atoms comes out to be very, very small. However, if I keep on increase the temperature of the gas, then at last a stage will come then when the number density of ions will exceed the number density of neutral atoms and plasma formation will take place. But this happens at temperature of the order of 100 million degrees centigrade, which is not available on Earth's surface. This is the reason the natural occurrence of plasma at high temperature is the reason for designated is the fourth state of matter. So this is important term in plasmas, which is Debye shielding. It provides the measure of distance over which the influence of electric field of individual charged particle is felt by other charged particles inside the plasma. In fact, whenever a positively charged ball is immersed in a sea of plasma, it will interact all the negatively charged electron cloud around itself. In fact, the negatively charged electron cloud will surround themselves in such a manner that they will shield the electric field of this positively charged ball to some finite distance. That distance is known as the Debye length, and the sphere so obtained is known as the Debye sphere. So these are the three conditions which every ionized gas must satisfy to behave as plasma. Firstly, the dimensions of the system should be greater than Debye length. This is because if the dimensions of the system are less than the Debye length, then in that case the charged particles will not have sufficient space for effective shielding to happen. So in that case, the bunch of charged particles will not qualify as plasma. Secondly, the number density of particles inside the Debye sphere should be extremely large. And thirdly, weakly ionized gas do not qualify as plasma, because in that case, charged particles collide so frequently with the vessel walls that the motion of the system is completely governed by collisions rather than by the electromagnetic forces. So let's discuss about the nuclear fusion in stars. Ancient astronomers thought that sun was a ball of fire, but now astronomers know it's basically the fusion reaction going on in the core of the star that allows us to output so much energy. Stars are the giant nuclear reactors. The core of stars is an intense environment, pressure is enormous, and temperature is also greater than 15 million Kelvin. But these are the conditions which we need for nuclear fusion to happen. Once these conditions are met in the core of a star, nuclear fusion converts hydrogen into helium through a multi-stage process, resulting in releasing enormous amount of energy. In nuclear fusion, lighter nuclei combine to give us the heavier nucleus, but the resultant nucleus has lesser mass than the sum of the combining nuclei. This difference in mass is converted into energy. The conditions for achieving fusion in laboratories are challenging because to bring about fusion, a new state of matter called plasma must be created. For creating a plasma, we need to heat a gas mixture at about 100 million degrees centigrade. At such extremely high temperature, the electrons get stripped from their respective nuclei, resulting into formation of ions and electrons. This ionized state is known as plasma. Now, since the like charges repel each other, the nuclei are kept apart. It takes even higher temperature to get nuclei in the plasma close enough to overcome that repulsion so that they can collide and fuse. However, reaching such a high temperature is not enough for fusion power to be relative. We must have enough fuel at that temperature for a long enough time for the fusion process to be sustained. The sun's gravitational confinement process on Earth takes place in two forms. One is the inertial confinement fusion, another one is a magnetic confinement fusion. So this is how creating a self-sustaining fusion reaction. In order to start a fusion reaction, you have to simultaneously achieve three things. Temperature should be high, keeping the plasma confined in a volume, and third one is prevent it from losing heat. Plasma confinement is the key to achieve fusion. Stars are so massive that they rely on gravitational confinement. But on Earth, nuclear fusion does not happen naturally. We rely mainly on two approaches. One is a magnetic confinement fusion, another one is the inertial confinement fusion. So in magnetic confinement fusion, since the plasma is composed of charged particles, so in presence of magnetic field, these charged particles are forced to move in a spiral path. In this way, we increase the confinement time. This isolation of plasma reduces the conductive heat loss through the vessel and also minimizes the release of impurity from the vessel walls into the plasma that would further cool the plasma. And in inertial confinement fusion, whenever high power laser beam is focused on a small target pellet which is composed of deuterium-tritium fuel, in that case the outer surface of the pellet reaches a temperature of about 100 million degrees centigrade, and this outer surface, 100 in 10 raised to minus 12 second, the shell of a pellet, now a hot plasma, it expands outward, pushes the fuel inward in such a manner, such a way that as the rocket exhaust pushes the rocket forward. In a very small time period, plasma expands and pressure on the pellet surface is about 100 million times that of atmospheric pressure. The fuel in the center of pellet reaches a temperature of about 100 million degrees centigrade and density is about 10 to the 19 per centimeter cube, which are the conditions which are favorable for fusion reaction. And once these conditions are met, nuclear fusion converts hydrogen into helium through a multi-stage process, resulting in releasing energy. This is how the inertial confinement fusion proceeds. Now, let's discuss about the role of laser plasma instabilities in inertial confinement fusion. The nonlinear interaction of high-power laser beam with plasmas has been a subject of active research on account of its relevance to laser-driven fusion and charged particle acceleration. Due to availability of lasers capable of delivering high powers, its interaction with plasma becomes a most interesting and important nonlinear problem. Various nonlinear phenomena like self-focusing, filamentation, scattering instabilities, harmonic generation might be generated from interaction of laser beam with plasmas. These instabilities affect the laser plasma coupling efficiency. Due to this, energy of high-power laser beam is not efficiently coupled with the plasma in order to keep the plasma. So it is essential to minimize this instability so that laser plasma coupling efficiency could be improved. So researchers are working on it theoretically as well as experimentally in order to keep this nonlinear phenomena at low level. So let's discuss about self-focusing and its types. It is a nonlinear optical process induced by change in refractive index of a medium whenever the medium is exposed to intense electromagnetic radiation. A medium whose refractive index increases with electric field intensity, it acts as a focusing lens for an electromagnetic wave characterized by an initial transverse intensity gradient, as in case of the Gaussian beam. The peak intensity of the self-focus region keep on increasing as the wave travels through the medium until the defocusing effects of the medium damage or interrupt this process. The nonlinearity in refractive index, which is responsible for self-focusing, can happen in plasma through three mechanisms. Accordingly, we are having three types of self-focusing. One is the thermal self-focusing, ponderomotive self-focusing, and relativistic self-focusing. Thermal self-focusing arises on account of collisional heating of plasma exposed to electromagnetic radiation. There is redistribution of carriers due to non-uniform heating, which leads to density perturbation and an increase of index of refraction, thereby leading to thermal self-focusing. Ponderomotive self-focusing is caused by the ponderomotive force, laser beam having variation in intensity along its wavefront. It exerts a ponderomotive force on electrons. In fact, it pushes the electrons away from the region where laser beam is more intense, that is away from the axis of beam. So the non-linear relativistic electric constant of the plasma, which is given by epsilon naught is equal to 1 minus omega p square upon omega naught square, it becomes maximum on the axis where electron density is minimum and it decreases away from it. In this way, plasma simply start behaving as a convex lens and it tries to focus the beam to a minimum possible diameter, leading to self-focusing of the beam. So relativistic self-focusing is caused by a relativistic increase in mass of electrons whenever electrons are traveling at speed comparable to speed of light. According to the equation, refractive index is given by 1 minus omega p square upon omega square under root. Since mass of electrons increases, plasma frequencies decrease accordingly. So as a result, refractive index increases. So plasma then simply acts as a convex lens and it tries to focus the beam to a small diameter, leading to relativistic self-focusing of the beam. So harmonic generation of harmonics of high power laser beam in plasma engaged the attention of a number of researchers due to its practical importance for many applications. It has a strong bearing on nature of laser propagation through plasmas because it allows the penetration of laser power to the overdense region and hence it provides valuable plasma diagnostics. And in case of second harmonic generation, the main mechanism is the presence of density gradients inside the plasma. The interest in the interaction of intense laser pulses with plasma is not only limited to harmonic generation because here excitation of electron plasma wave happens and this electron plasma wave interacts with plasma particles and it transfers its energy to the plasma particles via a particle interaction process, thereby exciting the plasma particles. So most of the work on harmonic generation is carried out in the past with the assumption of uniform laser beam, but the laser beams has non-uniform intensity radiance along their wavefront. So in such case, the phenomena like self-focusing, defocusing becomes important. So it becomes essential to incorporate the self-focusing effect while investigating this harmonic generation. So this is our main problem, impact of self-focused high power beam on second harmonic generation in quantum plasma. So in present work, impact of self-focused high power beam on second harmonic generation in quantum plasma is investigated. Relativistic nonlinearity results in the self-focusing of the beam, which gives us density gradients in transverse direction. These transverse density gradients results in generation of electron plasma wave at pump wave frequency. This electron plasma wave generated in turn interacts with the pump wave, giving us the second harmonics. So differential equation governing the propagation characteristics of laser beam with distance of propagation is derived by making use of Prexel approximation and WQAB approach. And this differential equation is solved numerically for investigating the effects of laser beam intensity and other plasma parameters on self-focusing of laser beam and second harmonic yield. And it is further observed from the analysis that introduction of quantum effects significantly impact the self-focusing of beam as well as the efficiency of second harmonics. So high power laser beam is considered to be propagating in thermal quantum plasma along z-axis. So slowly varying electric field is satisfying this equation. By making use of WQAB approximation, one may ignore the middle term. This will give us del square E plus omega naught square by omega C square of psi E equals to 0. Here epsilon is basically the dielectric function of the plasma, which is equal to the sum of two terms. Here epsilon naught is the linear term and phi is basically non-linear term. Now, considering the quantum mechanical effects, Fermi gas pressure and Bohm potential, the dielectric constant for the unmagnetized thermal quantum plasma takes the form this. Here, delta and beta are given by this. Beta is given by k square Vf square upon omega naught square. Here Vf is basically the Fermi speed and delta is given by pi 4 h cross square. I think by mistake I mentioned h, it's h cross square upon m naught square omega naught square lambda 4. So here TFE is, this is the Fermi temperature. Now, if I put beta equals to 0, I mean to say if I put Fermi temperature equal to 0, this thermal quantum, this is basically the dielectric function for the thermal quantum plasma. Then it becomes cold quantum plasma. And if I put both delta and beta equals to 0, then it is converted into classical relativistic plasma case. So the solution of this wave equation is of the form this. Now on substituting equation 5, 6, 7, 8 in equation number 2 and by making use of Prexel approximation, we finally obtain this second order differential equation. It tells us about how the laser beam is propagating inside the plasma. Here the first term is the diffractive term, second one is the nonlinear refractive term. Whenever laser beam transits inside a plasma, then there is basically relative competition between these two terms. It's basically the relative competition between these two terms that decides the focusing, defocusing behavior of the beam. When first term is dominating, in that case diffraction happens, and whenever second term is dominates, then in that case the beam self-focuses. This is how these two terms when diffractive and non-linearity both terms are present, and when second term is stronger, then beam focuses, and whenever first term is stronger, then beam defocuses, and when both these two terms are balancing each other, then this is the case of self-trapping. Now, excitation of electron plasma waves. For examining electron plasma wave excitation process, we need to focus on motion of plasma electrons only. So following standard equations may be used for investigating excitation process of electron plasma wave: equation of continuity, Poisson's equation, equation of state, and equation of motion. And following standard techniques and further making use of perturbation analysis, we can obtain this equation for the plasma wave generation. On substituting the value of E naught from equation number 6, here we get this second harmonic source equation, which is represented by this equation number 15. Now, generated plasma wave will interact with incident pump beam to produce second harmonics. The wave equation governing second harmonic generation is given by this equation number 16. On substituting the value of from here, we can derive the expression for E2, and it comes out to be this expression. And now, second harmonic yield is basically the ratio of second harmonic power to the power of the pump beam. And on calculating both the powers and on dividing the power of second harmonic by power of pump beam, we will obtain this efficiency of second harmonics. So we have used these parameters for numerical simulation of equation number 18 and equation number 9. So these are our results. Figure 1 shows the variation of beam width parameter versus the nominal distance of propagation at different values of intensity. Here we see that as we keep on increasing the value of intensity, we find that the focusing of the beam is increasing. This is due to the fact that whenever we are increasing intensity, then the second term is sensitive to this intensity parameter. So it keep on increasing relative to this. It starts dominating. As a result, the beam is focusing. And here the figure 2 shows the variation of beam width parameter versus the nominal distance of propagation at different values of plasma density. And it is again found that the self-focusing of the beam is increasing with increase in plasma density. This is due to the reason that when laser beam transits inside a plasma, then there is relative competition between these two terms. But if we keep on increase the value of plasma density parameter, then this second term starts dominating over first term, resulting in focusing of the beam. So this is a variation of beam width parameter versus the nominal distance of propagation at different values of Fermi temperature. And again, it is observed that if we keep on increase the value of TF, the self-focusing length of the beam is decreasing. This is again on account of the fact that with increase in value of TF, this refractive term starts dominating over diffractive term, which results in enhanced self-focusing of the beam. So this is our fourth graph, variation of beam width parameter versus the nominal distance of propagation at different plasma conditions. Red is for the classical relativistic plasma, green is for the cold quantum plasma, and this is for the relativistic thermal quantum plasma, blue one is. So again, if I put beta equal to 0, then we will obtain this classical relativistic case, and if we put delta equals to 0 also, then we will get the classical relativistic plasma. We find that as we shift from classical relativistic plasma to cold relativistic plasma, cold quantum plasma to thermal quantum plasma, the focusing behavior of the beam is increasing. This is again due to the fact that this term starts dominating over this term as we include these quantum contributions. So this is the graph showing the variation of efficiency of second harmonics against the nominal distance of propagation at different values of intensity. With increase in intensity, we find that efficiency of second harmonics is increasing. This is again on account of the fact that efficiency of second harmonics is basically directly proportional to the self-focusing of the beam. Since, as I told you in graph number 1, since the increase in intensity is increasing the self-focusing of the beam, as a result of which the efficiency of second harmonics is also increasing. Because amplitude of second harmonic generation will increase with increase in focusing behavior. So this is showing the variation of efficiency of second harmonics against the nominal distance of propagation at different values of plasma density. And again, it is observed that as we keep on increase the value of plasma density, efficiency of second harmonics is increasing. This is again because efficiency of second harmonics Y2 is directly connected with the self-focusing of the beam. Since Self-focusing is increasing with increase in plasma density parameter, so that's why here efficiency of second harmonics is also increasing. So the figure shows the variation of efficiency of second harmonics against the nominal distance of propagation at different values of Fermi temperature. Again, at high value Fermi temperature, efficiency is found to be more. This is again on account of the dependence of efficiency of second harmonics on second self-focusing term, which is increasing at higher Fermi temperature. So finally, we have the graph for the efficiency of second harmonics against the nominal distance of propagation. So red one is for classical relativistic plasma and blue one is for the thermal quantum plasma. And from thermal quantum plasma, we are getting higher efficiency as compared to the classical relativistic case. This is again on account of the fact that the efficiency of second harmonics is found to be more in thermal quantum plasma. So that's why here efficiency is also enhanced. So these are finally conclusion. Thank you very much.
We do have time for questions. Okay, I'll ask you one. It's often, well, sometimes considered in inertial fusion to add close to the target a magnetic field. And then the problem, it's often considered to add a magnetic field close to the target to enhance the fusion yield.
In inertial confinement fusion?
Yes.
That can be, case we also consider, basically this is unmagnetized case, we can also consider magnetized plasma.
Okay, so my question was, if you consider putting that into a magnetic field, the problem is usually that you get the illumination is not correct and it's elongated, it's asymmetric. Have you considered what the effect of a magnetic field?
No, here I have not considered, but that can be incorporated.
Do you have any idea how that would work?
I am working on that still. That paper is not completed. Basically, this is without considering magnetic field.
Okay.
Yes.
Another question? No. Then we are right on time, and thank you very much.